sound reverberation, the time it takes for loud noise to get not loud. So this is the basic speed of sound formula, but it's not really a perfect approximation. So C is the speed. I think that's rho is the specific heat, also the pressure, and the density over the density of air, all under square root. This isn't a great approximation, so I decided to make it worse. So using the ideal gas law, we can approximate a better speed of sound formula. And so we substitute out a little bit. So we get speed of sound is square root of lambda times Boltzmann constant, which I'm just going to write up on the board for you because that's going to be on your quiz. Or, wait, is it on the worksheet? I don't remember. Is Boltzmann constant on the worksheet?
No, it might be at both
You can
sides.
erase it.
Okay, then I'm going to put it like right here in green. Yeah, it's that. Basically, it's temperature into raw heat energy, and temperature in Kelvin. The M is the mass of one molecule or one atom of a substance in kilograms. And you divide by Avogadro's number, and yeah, you get that, which I don't think that's on the bookmark either. I promise it gets better. Okay, so now that we've got the speed of sound, now you just have to find the time it takes to get quiet given the size of a room. So this is going to be the length, and this is going to be height 1 and width 1. This is going to be height 2 and width 2. Or I think I converted it to area 2 and area 1. And so the basic unit of time is the time it takes to go, is it middle to go back? Yeah. Time it takes to go down and back. That's going to be what we're using for time. So that will be T. And all of the measurements are in meters. And moving on. So after a time span of T, area 2 over area 1 of the sound is lost. The proportion measuring between this area over this area. And yeah, I just have it down there.
So what does it mean that that sound is lost?
It gets quieter. That energy is lost. I don't really know how to describe it. It's like the sound of my voice, you don't keep hearing it over the span of a minute. Unless I keep talking. So if that much is lost, that means 1 minus that proportion remains. And assuming since it's a window, the proportion will always be lower than 1. And after 2t, this much more sound is lost. So in total, that much sound is remaining minus that much sound is lost. Yeah, so I basically, oh yeah, I did that. It's Old Man Walker, but you can't hear. So you distribute to make it 1 times that proportion and A2 over A1 times that proportion. And then you take these and put it next to each other because you, again, distribute because these are the same. And you end up getting A minus A1 over A2 over A1 squared. And so then we can get after NT passes, A minus A2 over A1 to the nth is lost. Yeah. And so that's just the formula described. Alright, so now we're finding when the sound is like actually quiet. Don't worry, it's almost over. So if we want to find when the sound completely disappears, we're going to want to find when it's 1 millionth of the original noise. So that's 1 over 10 to the 6th. And now it's time to use logs. So if it's 1 over 10 to the 6th, that's 10 to the minus 6th. So then we take the log of this is negative 6 is n log A minus AT over A1. So if A is A2 over A1 is much lower than 1, you can approximate the formula. So you divide the left by n and divide the right by 6 times A1 over A2 to get this. And if we do that, we can approximate n to be equal to n equals 6 A1 over A2, because that's what we divided by up here. And now we're going to derive this bottom formula. So if T is what we found earlier, 2L over C, and N is what we just found, 6A1 over A2. We multiply them together to get the formula for NT. So it's 2 times LC times 6, A over 1, multiply the 6 and the 2 to get 12. Then you multiply the L by the A1 and the C by the A2, because they're both on top and bottom respectively. And then final formula is 12 length times the area of the wall over speed of sound times the area of the window. And because it ends up being length times the width of the wall times the height of the wall, you can turn that just into the volume of the room. So it turns into NT equals 12 volume over speed of sound times area of the window. And since sound isn't just traveling one direction, it's traveling kind of in a cone-ish, it needs to be modified. I didn't actually have a way to find this out specifically on my own, so I just followed some guys who are smarter than me. W.C. Sabine and W.S. Franklin, they found experimental values of this constant being 55, so I'm just gonna go with what they said. They're the big guys on the playground. They make the rules, not me. So our final formula is 55 volume of the room over speed of sound times the area of the window. So just to recap, speed of sound in normal air is square root of lambda times this times the temperature in Kelvin over this number. And travel time is T equals 2 times the length over the speed of sound. Sound remaining after N of T is 1 minus A2 over A1, length of the window over length of the wall, or area of the window over area of the wall to the power of N. And the time for the sound to dissipate is 55 volume over the speed of sound times the area of the window. Any questions?
I was promised English.
This is all you'll need.
So they're on the Google class where you just copy those formulas. All you're gonna do is put the numbers in that Drew has. So it's up to you if you wanna copy these down now or just take them off the PowerPoint.
I'm just going to leave these up here.
Yeah, leave them up, yeah.
Okay. Any questions? Wonderful, and I'm sorry.
Anna,
What?
you're next.